Hey there, AP Biology, and welcome back to our Chapter 7 discussion on cellular respiration. I want to start off with a quick misconception alert. I know that this phrase is probably the one thing you remember from middle school biology, where you said the mitochondria is the powerhouse of the cell. And little problem I have with that phrase. Mitochondria is not the powerhouse of the cell, but mitochondria are the powerhouses of the cell. Mitochondria is plural. If you're referring to an individual, a mitochondrion is the powerhouse of the cell. But even with that slight grammatical fix, in AP biology at least, I would avoid this phrase. If you write it on an FRQ, graders aren't going to give you any points. It's too simplistic in what it's describing. So in the future, make sure you're talking about how mitochondria participate in cellular respiration. And even better, mitochondria convert sugar like glucose into usable energy like ATP. So let's explore how this actually happens. So this reaction of cellular respiration, we're going to eat some sugar, or C6H12O6, our simple glucose molecules, and we're going to breathe in some oxygen, 6O2 molecules, and then we're going to have a combustion reaction that's going to leave us with 6 carbon dioxide molecules, 6 water molecules, and then a bunch of energy that we're going to be able to store in the form of ATP, or our cellular energy currency. Now, I'm leaving all these numbers out here because throughout this chapter, you're going to kind of play the role of an accountant. If you've got stuff going in, you need to make sure you've got it going out. And you want to see where you're gaining things and where you're losing things. So as you look at this reaction, I have 2 questions for you. Is this going to be anabolic or catabolic? And is this reaction going to be endergonic or exergonic? Take a moment. That's right. It is catabolic because we're taking a large complex molecule and breaking it down into smaller simple molecules. And then anytime you have more energy on your product side than you have on your reactant side, or at least more free usable energy, because that energy is just getting converted, that is an exergonic because we're releasing that energy. Now, this reaction is not as simple as that equation would lead you to believe. Inside your cells, there's actually a multi-step process. The 3 biggest phases of that are going to be glycolysis, happening in your cytosol or outside the mitochondria, the citric acid cycle, and then oxidative phosphorylation. And this is going to be the big one that gets you most of your ATP. But you can see that every step is going to generate ATP. And then those steps are going to generate something called NAD and FAD, or electron shuttles, and we'll explain what those do. So you might be asking, why are we going about this business of making ATP? Why don't we just use sugar? Well, like you saw with all those reactions, getting sugar out of or getting energy out of sugar is a really complex reaction, and it's really hard to control. So it's not really well suited for simple, quick energy use. So then why do we even bother with sugar? Why aren't we just only using ATP? Well, ATP is way too bulky for storage, for how much energy you get out. Sugar holds more energy for its size. So we can store sugar for some short-term storage purposes, and then we'll convert it to ATP for having a reserve to actually burn. So, like I mentioned, it's hard to control sugar. If we go straight from sugar to energy, it's too explosive to contain. But if we do a stepwise function, we can very easily control releasing it and building ATP. So, the reactions that are going to be taking place are going to be called redox reactions, which is short for reduction oxidization. And these reactions are anytime electrons are transferred from one atom to another, or one molecule to another molecule. So one molecule is going to get oxidized, or it's going to become more positive and lose an electron, and one is going to become reduced or gain an electron. Now, this may seem counterintuitive. If you're gaining something, why are you getting reduced? Well, reduced refers to the charge. So, because electrons are negative, if you gain an electron, you're going to become more negative. Your charge goes down, or your charge is getting reduced. A simple way to remember that, though, Leo goes grr. So, if you can remember that Leo the lion roars grr, you're going to remember that lose electrons is oxidation and gaining electrons is reduction or being reduced. So Leo goes grr will help you clear it up if you can remember that. All right. And who's going to be doing this oxidizing and reducing? Well, that's going to be a coenzyme called NAD and FAD, or NAD plus and FAD, that we refer to as electron shuttles. And what they're going to do is those first two reactions I mentioned, glycolysis and the Krebs cycle, all the stray electrons as we're converting energy and matter from one form to another, it's going to be grabbing these high energy electron particles and it's going to carry them all or shuttle them all to the final step where we're going to use those high energy particles to generate a ton of ATP. So these are going to be really, really important for us down the line. All right, that's it for our first video. Catch you next time.